Now that you're a veteran finding area with polar curves with one curve, we're going to move on to doing it with two curves. A brief reminder from a previous video or previous learning. When you have one curve, in this case it's making a loop, you get your area by just essentially drawing a series of radii to every spot along that curve, and that shading that you get when you do that, as long as you put it into some sort of sound mathematical form, which you'll memorize, you're going to go ahead and get that area. Well, in the case you're looking at here, we've got two beautiful circles. 3 sine theta makes a perfect circle. 3 cosine theta makes another perfect circle. We're looking for the area caught between the intersection of these two, like a good old-fashioned Venn diagram. So for a moment, ignore the teal bluish circle and just think about this red one, 3 sine theta. If I think about different spots along the way, this curve is kind of built by drawing a radii to all those different spots. And as like we talked about in the previous video, if I were to put those spots so close together and I just keep drawing those radii, essentially we're filling in the entire border of the circle. And as I do that, I'm getting closer and closer to this intersection spot. At that point, I'm going to stop. If I keep drawing lines or radii out to the border of the red curve, eventually I have to start drawing to places like this. Well, if I draw that, you'll notice that my radii extends beyond the region that I'm trying to find the area of. It was this area, and this radii would be naughty because it would be living out here, getting us too much area. So what I have to do at that intersection spot is I have to notice that I'm really switching from the red to the blue curve. So as soon as I get there, now I start drawing my radii to the blue curve, and you'll notice the same thing. If I go to every single point along that curve, I'm shading in the top half of that section. So the area that I'm trying to find is really the addition of some blue and some red. The blue are radii drawn to this blue curve. The red are radii drawn to the red curve. As long as I grasp that and know the intersection spot, which is the point when I need to switch over from the red to the blue, life is going to be good. So I'm going to get to the actual integral here in a moment, but I want to take a second to talk about this intersection point, because you may have some grief finding that intersection point, maybe, maybe not. So I have a little bit of advice. First of all, your main strategy is hope that they give you that intersection point, and very frequently on the AP test they do. But let's say they don't give you that intersection point. Then you're going to probably either do some version of trial and error with your calculator. This is some better trial and error with your calculator, or resort to good old-fashioned algebra. So I'm just going to show you what I mean by a few of these. I got to set up my calculator. Okay, by the way, as I look at that intersection spot, it looks like my gut instinct would be it's located along this trajectory, which you would probably guess as well as me that that's a trajectory of pi over 4. And, I'll spoil it here. That really is going to be the trajectory. But let's pretend you didn't know or you weren't certain. For my r theta, the theta is pi over 4. I'm not sure what my r is in this case, but I don't think it's going to matter for us. All right, but if I wasn't confident in the pi over 4, here's some strategies. In polar coordinates, I graph them, making sure I have a good window. I see the region I'm working with. I see the intersection spot. I could get a feel for it by just simply hitting trace and then moving my turtle around the circle. And the trace is rarely going to give you an exact landing spot. In this case, it actually did, but you wouldn't be certain anyway. But you can trace, you can go around either circle, and you get an idea by looking right here at the theta about what the trajectory would be. But if you want to go a little bit closer, you can use the value or the table. You can always go second, calc, and choose a value. And now if I plug in, if I suspect it's pi over 4 and I plug in pi over 4, my turtle seems to be on the intersection point, so it's probably pi over 4 as I suspected. But I can also do this. I'm going to setting up the table, and I'm starting at 0. And in this case, since I'm suspecting that it's at pi over 4, I'm going to make my table go by increments of pi over 4. And now this one's going to give me a firm conclusion, not a I think so conclusion, because now if I look at the table, at theta equals pi over 4, the radius of my two curves are identical. So this gives me undisputable proof that it is pi over 4. But I'm going to show you other strategies. For example, you could go, I'm going to go to the function mode. And now what I'm going to do is I'm going to take my two equations and I'm just going to see where they intersect on function mode. I might have to reconfigure my window. Let's find out. There's one of the curves. There's the other curve. They're intersecting. If I find out where they intersect on function mode, that's the same thing as where they intersect on polar mode. So I would go second, calc, intersect, and do my thing, which is hope that the calculator does its thing. And of course, math is math. We get the intersection point in decimal form, pi over 4. And I'm going to give you one more option. Let's say it was not a calculator problem. You could use algebra. So in this case, I'm saying, when does 3 sine theta equal 3 cosine theta? Because that shows the two curves intersecting. Reduce the 3's. When does sine theta equal cosine theta? Well, this one's as easy as thinking about the unit circle. Where on the unit circle are sine and cosine equal? Here they are, and here they are. So at that spot, pi over 4, I have my answer. So a lot of different ways to figure out that intersection point. That's probably the way it's going to happen on the AP test, but there's no guarantee. So now let's go back. After all that work for talking about the intersection point, let's go back and figure out how to get a value for this area. And when you do that, what you really have to remember is that what you've done here is you've done the area within one curve with the red one, then you've done the area within one curve on the blue one, but we're just combining them to get the area that happens to be between both of those curves. So here it is. My total area is the area carved out by my red drawings. 0 to pi over 4, we took so much work to find that pi over 4, of, I'm just using the formula, 1/2 r squared d theta. If I put that 1/2 outside the integral, I have to remember to multiply by it at the end. Now I go at this spot, my radius transfers to being drawn to the bluish one. So now I go starting at pi over 4, because that's where I left off. Uh-oh, we didn't come up with the ending limit, but it's still a 1/2 r squared d theta. So now we have to do some thinking about the ending. If I think about drawing all these radii, my last one is right here, vertical and basically 0 length. Well, you're pretty sure that's pi over 2, and you're right. And one thing I have to say is when you have spots near the origin, you have to be careful, because this spot could be the trajectory of pi over 2 with 0 length. But really, couldn't this spot be the trajectory of pi in 0 length? It really could be. In this case, it's what your instincts tell you, but I'm going to show you how you can confirm this in a second. I'm I'm not going to bother computing this number, but it does. This whole mess turns out to be a number. You would have to switch into function mode to get that taken care of. So just a quick tip to show you how you can confirm that pi over 2 ending spot. I'm back in polar coordinates, and with this blue graph, that's the cosine graph, so I'm going to deactivate the other one and activate cosine. I'm going to graph it, and we're concerned about the value of that spot. Many different ways to get it done, but here is a way that kind of helps. It's informed trial and error. So what I can do sometimes is I say, hey, I suspect that's at pi over 2, so I'm going to have my calculator graph just to pi over 2. See what happens. It's exactly what I thought. It stopped at pi over 2, which makes me believe that that's pi over 2 location. That's the ending spot. That's polar area with 2 curves, part 1. Because we can have 2 curves and a different style of thinking. That's coming up in the next video. See ya.